Hey there, welcome to Pomodoro Joe for Wednesday, October 25th, 2023. Today we're looking at LeetCode problem 779, kth symbol in grammar. This is a medium problem. We build a table of n rows, one indexed. We start by writing a 0 in the first row. Now every subsequent row, we look at the previous row and replace each occurrence of a 0 with a 0, 1, and each occurrence of a 1 with a 1, 0. For example, if n is 3, the first row is 0, the second row is 0, 1, and the third row is 0, 1, 1, 0. Given two integers, n and k, return the kth, that's one indexed based, symbol in the nth row of the table of n rows. Okay, so we're given two numbers, n and k, they're integers. N is the number of rows, and k is the index of the kth symbol that we're trying to return. Now it's going to be either a 0 or a 1. And it looks like with n being 1 and k being 1, well, we only have one row and it's got a 0 in it, so we return 0. All right, n is 2, k is 1. Well, the second row, as we saw up here, it's going to be 0, 1, so we return, let's see, 0. Because it's one indexed based. All right, so we return 0. And then finally, n is 2, k is 2. So with n being 2, again, it's 0, 1 for our row, but k is 2, so that's 1, 2, and we return 1. All right, so let's put 25 minutes on the Pomodoro timer and we will get started. So this seems pretty straightforward, actually. We just did a problem yesterday, where we go through a tree and we are doing a level order traversal. This is very similar. We're going to build our row. So this is kind of like a tree. The first row has one element, second row has two elements, third row has four elements. So it splits into two for every level down, very much like a tree, a binary tree. So in our first row, we're going to have 0. Then in our second row, we're going to have 0, 1. And we'll actually keep building up our rows. So we'll start with our current row, we'll build up the next row, then we'll swap it out. So it's very similar to yesterday's problem with the level order traversal of a tree. So let's do this. So let's start with our current row. And it's just going to be equal to, I'm going to use strings here. So we're going to set equal to 0 to start with. And we have our next row. Actually, we'll get to our next row in a little bit. So current row is 0. So let's see, we also need our row index. That's going to be equal to 1, because this is a one indexed based system. All right, so while our row index is less than n, so we're building up these rows, our next row is going to be an empty string to start with. And now we'll be going through all the characters in our current row, and we'll be, I guess, building up our next row. So for every character in our current row, if this character is equal to a 0, well then our next row in this spot, we will, let's see, add, according to this, if it's a 0, we'll add a 0, 1. So we'll add a 0, 1. Otherwise, this character must be a 1, so our next row will add a 1, 0. All right, and once we go through all of these characters in this row, we'll swap out our rows. So our new row becomes our next row. All right, so we just assign our row to be what this next row is, and then we have to increment our row index, so then we don't end up in an infinite loop. All right. And that should do it. Then at the very end, we'll have our row equal to, I guess, the characters that we're looking for. And we just have to index into k. So for this, we'll return our row. And since this is a 1-based system and our row itself is 0-based, we have to go k minus 1. So if k is 1, we return row index 0. Okay. And I think that's it. Let's see if this works. Oh, because I'm using characters here and they're looking for integers, all right, we do need to convert this into an integer. So we'll call this an int. All right, seems to work. Let's submit this and see how we do. Time limit exceeded. We'll use this test case, but let's look at it first. N is 30, and look at this K. That is huge. We're building a string that is this long. That's going to be a problem. All right, so just looking at this value for K, I kind of think this is not going to be a valid solution. If we actually need to build up a row that has this many characters in it, we're definitely going to run out of time, and we're probably going to run out of memory. So we need to find a better way to do this problem. Now, in this current solution, we're actually building up all of these rows. Now, we already know the K, that's the target that we're trying to get to. We don't need to build up the entire row just to find this one character in that row. Now, as I mentioned before, this entire system is kind of like a tree, like a binary tree. So what if we didn't actually build up all of these rows, and instead we just followed the path in our binary tree from the root, that's row 0 here, or row 1, all the way down to our kth character. So in that case, if we start at row 1, we have a 0. We either go to the left or we go to the right. So for the next row is either a 0 on the left or a 1 on the right. So we'll go down to the next row. We either go to the left and it's another 0, or we go to the right and it's a 1. Then from that row, we need to go to the next row, and we either go left or right. And we keep just going down our rows left or right until we get to our target index, which is K. Okay, so this is a little bit trickier, but I don't think it's too bad. So my plan here is to think about, well, the very last row. So like this row that has this many characters in it. So in our very last row, which is row 30, since this is a binary tree and every row doubles in size, that means this is going to be 2 to the 30 minus 1 number of leaf nodes. So in our very first row, or our level, let's call it levels. So in our first level, we have 2 to the 0, that's 1 nodes or characters. In our second level, that's going to be 2 to the 1, 2 to the first power. That's 2 nodes, all right? Then in our third row, we're going to have 2 to the 2, so that's 4. We'll have 4 nodes, or 4 characters, and so on and so forth until we get 2 to the 30. So it's actually going to be 2 to the 30 minus 1, so 2 to the 29. That's a lot of characters. But since we know how many characters are in that row, we know half of them are a result of going to the left at the very beginning, and half of them are a result of going to the right at the very beginning. So our tree will lead down to one of these characters. So all I have to do to figure out is if I have 2 to the 29 total nodes or leaf nodes, total characters in this row or in this level, where does K fit in? Is K in the left half or in the right half of that level? If it's in the left half, that means I know when I made my first move, I had to go to the left. From my root node, I had to go left. If it's in the right half, that means I know from the root node, I had to go to the right. Next, we go up to the previous level. Where is our K in that tree or in that level? I do the same thing, figure out how many nodes are in that level, figure out if it's in the left half or the right half, and then work my way back all the way up till I get to the root. So I'm kind of working my way backwards here. Okay, so let's start this whole thing over. All right, so I'm treating this now like a binary tree. So I'll have a level, and we're going to start at level 0. Actually, no, we're going to start at the end. So we're going to start at level n. So we're starting at the very end. And then we'll have our index that we're looking for, and we're going to have K as our starting value. So this is our target, level n, index K. All right, so while we still have some level, because we're working our way backwards, so while we still have some level, let's find the midpoint of this level. So the midpoint of this level is going to be 2 to the, and that's going to be our level, minus 1. All right, so in this case, they're telling us we have a 1-based system. Right, so level 1 is going to be our very first node. I'm actually treating this more like a 0-based system while we have some level. So in the end, we're going to get down to level 0. So in order to treat this as a zero-based system, we have to do 2 to the, how do I describe this? So I'm saying our root node is at level 0. So with our root node at level 0, that means we would have 2 to the 0 nodes, which is 1 node. At level 1, we would have 2 to the 1 nodes, which is 2 nodes. At level 2, so on and so forth. Now, in order to find the midway point, we actually want to do 2 to the level divided by 2, right? So if we wanted to find, let's say this is level 30. If we wanted to find the midpoint at level 30, that would be 2 to the 30 divided by 2, which is really just 2 to the 29th. So in that case, I can just say 2 to the level minus 1, and that will actually give me the midpoint at this level. So let's find the midpoint, and then we're going to check our current index. That's this k. Where is our index in relation to this midpoint? So if our index is greater than this midpoint, that means we must be to the right. So from the very first move, we had to have gone to our right node first. So I'm going to keep track of our directions here. Let's actually keep that out here. So we're going to have some directions list. And I'm just going to make it a string because that's easy. So we're going to have some directions. Which direction did we have to go in order to get to this point at this level? So for this, we had to go right. So I'm going to just add, let's see, I'm going to use characters here. We had to go right. All right, otherwise, we're on the left side, we had to go left. Okay. All right, and now we move down our level. So level minus equals 1. All right, but there's one thing we still need to do. If we came from the right, we need to fix up our index here. So we need to, how do I put this? So as you notice, I'm not keeping track of the left or right bounds or the upper lower bounds on each level. So that means in our very last level, when we're looking for this k, it's fine because we're in with, how do I put this? In the very last level, when we're looking for our k, we don't have any, our bounds are basically 0 all the way to 2 to the level minus 1, or 2 to the level actually. 2 to the level parentheses minus 1. So those are our bounds. When I move up to the previous level, I have to readjust my bounds. If I came from the right-hand side, we're not starting at 0 anymore. We're starting at some midpoint up to the upper bound. So I do need to adjust my index here. So my index actually has to be adjusted by this midpoint. Hopefully this makes sense. It's a little bit more mathy, or I wish I could draw a diagram, but basically, let's say we were to the very right on our last level. We came from the very right-hand side, somewhere on the right-hand side. When we move up to the previous level, that level will have 2 to the level minus 2, or this new level, I guess, 2 to the new level minus 1 nodes in it, but it doesn't start at 0. It'll start at 2 to the level minus 1. So I need to readjust my entire index by this current midpoint so that we're re-zeroed. I can't describe this. Hopefully this makes sense. I'm sorry, this is a mess. All right. Now that we've gone through, so we're going to go through all of our levels, we're going to compare where is this k compared to our midpoint at this level. Did we have to come from the right or the left here? Okay, we've built up our directions. This is kind of working our way back up to the root. Now that we've worked our way back up to the root, we basically have to start at the root and work our way back down to this k by following this map, our directions. So let's have some node. We're going to set it equal to 0 because that's what our first row is equal to. So we'll set our node equal to 0. And then for every direction in our directions, we'll just check, do we go left or do we go right? So if d is equal to left, I'll be consistent with my, all right. So if the direction is left, well then we'll just continue. Oh, I should describe this. Okay, so we're starting at 0. Let's actually maybe draw a little diagram here. So we start at 0. Let me do it this way. Value left right. So the value of our node, if it's 0, right, then our left, as we can see over here, our 0 becomes a 0, 1. So the left is a 0, and the right is a 1. All right, and if our value is a 1, this tells us our left is a 1 and the right is a 0. Okay, so this is our little truth table here. So if our node is 0, 0, and we're going left, it stays 0. If the node is 1 and we're going left, it stays 1. So if we're going left, our node value doesn't actually change. But if we're going right, then if we were 0 and we go right, we become a 1. If we're a 1 and we go right, we become a 0. So we actually have to flip our nodes. So the node will equal essentially not node, but since not and 1, since 0 is not the opposite of 1, I basically have to do a check here. So this will be a 1 if the node is equal to 0, else it's a 0. Okay, again, hopefully this makes sense. If we're going left, our value doesn't change because you can see these two columns are the same. If we're going right, we have to flip our values. So you just flip them and move on. Now at the very end, once we go through all of this, we can just return the value of our current node. All right, this is kind of tricky. It's difficult to describe. So the essentials, we're down to 6 minutes. Let's see if this works. All right, let's see if this works and then we'll review. Okay, it seems to work. Let's see if we can pass all the tests. And we pass. Okay, and we do okay. We beat 85% for runtime and 97% for memory, so that's really good. All right, let's do a quick review here. In our first attempt at this, we just built up every level. So we had our current level, our starting level, which was 0. Then we just go through every character in our current level, building up our next level. Once we get to the very end, we just find the index, index k, in that level and return the value. Unfortunately, that was too slow and too memory intensive for very large values of n. So our new approach is, instead of building up every level, we're just going to follow the exact path we need to get to our index k at the nth level. In order to do that, we actually had to build up this direction map from the endpoint back to our root. So we start at the very lowest level and we look at the midpoint. Where does our k, our current k, fit in this level? Is it to the left or to the right of our midpoint? Then we look at the next level or the previous level. We have to adjust our k if we came from the right. If we come from the left, it's still 0 based, so we don't have to make any adjustments. Then at that level, did we have to come from the left or the right? And we just keep looking at previous levels until we work our way all the way up to the root node. This is very much like a binary tree traversal in reverse. Now that we've built up all the directions, we'll go back down from the root node, starting with value 0, and we'll just follow our direction all the way back down to our kth index in the nth level. All right. Well, I wish I had a better way to describe this. I wish I had some diagramming software that I could show you how this works. It's kind of tricky to describe. If you get a chance, try this on your own, then check out this editorial page. I think they have a pretty good description of this particular solution. All right, well, that's it for me. I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.